state the question and draw an arrow or whatever it is you need to do. That way when you go back and study these things, you'll know that. Because you know if I'm asking it at this point, it's probably going to come up again, right? So, which area within the entire neuron is where you will see the sodium-potassium pump being activated? So what area or areas, plural, would you find the sodium-potassium pump? All right. Follow-up question. When the sodium-potassium pump is activated and sodium moves into the axon, what do we call that process? When sodium moves into the axon and changes the electrochemical gradient, what do we call it? Follow-up question. Before sodium moves in, your neuron has a resting membrane potential of what? What measurement in millivolts is your resting membrane potential? Last question. See if you're really paying attention. When we charted the membrane potential over 8 milliseconds, when sodium moved in, millivolts went up. What was that number at the peak of that measurement? Any of those need to be repeated? All right, so what we're focusing on, again, is just kind of reviewing how these are being communicated, but really looking at it at the cellular level. So let's see how we did. Go ahead and check your work. So up here, you should have dendrites, and what we said the other day is that you have multiple dendrites because you have multiple neurological pathways. I stated to you that every single one of your functions that you carry out has a very specific neurological pathway. So those dendrites act as neurological receivers. They're bringing messages in. And what we clarified is that this is a one-way street. It always goes from your dendrites to your axon terminal. We're going to talk about the axon terminal today. All right, then we go down here, cell body, nucleus, mitochondria, all that, axon hillock. There's your axon. But then what you should have identified is all these small exposed areas of the axon are called your nodes of Ranvier, which is also the source of the sodium-potassium pump. So those are the only locations where you're going to find the sodium-potassium pump. What you should also have are Schwann cells. Schwann cells are what coat and insulate the axon with what we call a myelin sheath. It insulates it, prevents signals from jumping from one neuron to the next. A good example of the Schwann cells is autoimmune diseases like Alzheimer's, MS. Those are what we call demyelinating diseases. And so when you lose that sheath, you can lose that signaling. So what you see in a lot of patients that suffer from those terrible diseases is that their brain is actually sending the message, but the message isn't being received. It's being lost. So the message is sent, but at some point along that pathway, it's getting lost because it's not insulated with that myelin sheath. All right, and at the very end, you have your axon terminals, which we're going to focus a little bit more of our attention on today. So what we did say is that your transmission of your sodium-potassium pump is going to occur at the nodes of Ranvier. When sodium moves in, what do we call that? Depolarization. Depolarization. So there's depolarization, and then there's repolarization. So depolarization is where sodium's moving in, which causes the millivolt measurement to rise. At resting membrane potential, you should have had negative 70 millivolts. The maximum is 50, positive 50 millivolts. So make sure you really study that graph that we went over, because you're going to have some questions over this quiz over the weekend that are going to really be addressed right at that graph. All right, how do we do on this? Pretty good so far? All right, so we're going to carry this conversation on a little bit more today. So what I'd like you to do at this time, go ahead and get out that packet for me that we've been working on. Let's get that out. And on that packet, go ahead and turn to the very back page. It looks like this. Actually, it's the exact image. Yeah, well, the whole thing is the axon terminal. Terminal just means the end. All of these are bulbs. Yeah, those pictures tend to be a little vague. I'm not going to worry so much about those specific names, just what's happening there. All right, so our goal for today is to really kind of dive deeper into this communication, because really all we've talked about up until this point is this. And we've already watched this, but we're going to watch it again. All right, and this is kind of what we were saying the other day is, can you explain what you're seeing in this video now that we've talked about what we've talked about? Okay, so you see all these neurons firing. So now at this point, zooming in on an axon. Okay, so right here, see how all these ions are moving out? Those are your sodiums. And then they're going to move back in. So right now, as they move out, do we call that depolarization or repolarization? Repolarization. So when they move out, it's repolarization. When they move in, they're depolarizing. And the reason why that matters is that changes the electrochemical gradient and sends the message in one direction. So this is kind of analogous to squeezing a tube of toothpaste, moving it all in one direction. So we'll keep watching here. So depolarization. These are your sodiums right here. Being pumped back in, now pumped back out by the sodium potassium pump. Okay, now we're going to start getting to the good stuff. Alright, now I'm going to have to turn the lights off for this one, so try and stay away from it. I'll try and go quick, but we also, oh, that's really dark. Okay. Is that okay back there? Everybody? Okay, good. Now, what are we looking at? Now, you have the picture in front of you, kind of the same version of it, but what we're going to talk about is what we call ligand-gated ion channels. And the only way this works is that these ligand-gated ion channels have to be signaled to open. And what we're going to see in here, this is our second type of communication. So at this point, where we're at on our neuron is we are now reaching the end, what we call the axon terminal. And within the axon terminal has all these tiny little bulbs. Within those bulbs, they have little vesicles here that you see all over with these little red dots in there. Those red dots symbolize neurotransmitters. Neurotransmitters are tiny little proteins. Those are your ligands. So when we think about a ligand-gated ion channel, the ligand here are your neurotransmitters. But those neurotransmitters don't affect the synaptic bulb here. They're going to affect what we call an adjacent neuron, or what we call a postsynaptic. So what I'd like you to do here, first and foremost, this area is what we call a presynaptic neuron. Now, all that means is that this is the first line of communication. So what you see here in this adjacent neuron, or it could be a junction of some sort of muscle, an organ, something like that, we call this the postsynaptic. All right, so you have pre and post. This is just telling us where the communications are going. Now, as we look through here, you see this area is becoming depolarized. Kind of this white, cloudy nature of this image is showing us that's where the sodium has moved in. And as we've already said, when sodium moves in, that's depolarization. Everybody with me so far? So we change the electrochemical gradient, and by changing the gradient, we change that permeability. Why does that matter? Well, this is where I introduce to you our next secondary messenger known as calcium. Calcium is absolutely vital to this, because if all of these vesicles in here are housing neurotransmitters, the question has to be, how do they get out? And that's where the calcium comes in. What calcium does is it floods into the synaptic bulb. And all of these vesicles that are normally just chilling, I mean, they're just hanging out there. And you see all these purple structures? You should already know what those are. Who wants to tell me? They're part of the cytoskeleton and for movement. Not filaments. These are microtubules. So all of these vesicles, kind of like a train on a rail, they're just going to move right along on that microtubule. But that's where the calcium comes into play. It's going to activate this process. Now, I'm not going to bore you with all of the kind of the nuances of how that actually works, because that's not really what we need to know. We just know that these vesicles will not move without the calcium. So that's why the sodium has to be the primary message. The primary message is that sodium flooding in, depolarizing. And then at the end, when it gets to the end, it depolarizes so calcium can flood in. And then these start moving. Now, here's where it gets, I think, very, very interesting. If you look at your image, you have this gap between your presynaptic neuron and your postsynaptic neuron. Many of you have heard of this before, and this is why we call it synaptic signaling. This is what we call your synaptic cleft. All right? A cleft is a space between two different objects. Now, this synaptic cleft is significant because when we look at these neurons never physically touch each other. So, if they never physically touch, I'm going to ask you a question. Do you think the space between the presynaptic and the postsynaptic neuron, do you think those matter? Do you think we should be able to measure the distance between neurons? Of course, the answer is yes, or else why would I be asking you, right? Well, here's my question. Think in your head something that you tried for the first time and you were great at it. Anybody coming up with anything? Ooh, Essence, what you got?
Cooking.
So the very first time, you knew exactly how to turn on the oven, and you were cooking like an Italian grandmother, not even reading the recipe, just throwing stuff in there, acting like Emerald, boom, doing all that.
Well, potato salad, yeah.
Was that really cooking though?
I mean,
I think cooking like spices, and you got the hat like Ratatouille, just going to work.
For first time without a recipe. I just didn't agree.
All right. So, what was it? You made potato salad? Was it good?
Yeah, my grandma said it was good.
Well, grandma approves, then you know it's good. You know what I mean? All right, so besides Essence being awesome at making potato salad, did anybody else come up with anything that the first time they tried it, like, yeah, I'm pretty spectacular? Did anybody come up with that? How many of you, when you rode your bike for the first time, you were just cruising, doing tricks? Yeah, I didn't think so. The reason why, and maybe we need to study your brain a little bit because figuring out how the cooking apparatus works, but the point I'm making to you is this. I shared with you the other day, every time that I teach you something new, or any other teacher, or just life in general, teaches you something new, you are literally creating a new neurological connection. But the repetition of that neurological connection is what matters, not volume. And yes, I'm gonna piggyback this into your study habits. If you told me that, hey, I studied for 5 hours at the dining room table the night before a quiz. All right? 5 hours, 60 minutes, 300 minutes. All right? Everybody, is that good math, right? Is that right? Just making sure I'm going fast here. So that's 300 minutes of study. That's a pretty good flex, right? Sounds good. I studied for 300 minutes. But then you get a teacher like me who says, well, that's pretty stupid. Why don't you study 10 different times for 20 minutes? So wait, you're telling me I should only study for 200 minutes instead of 300 minutes. Now, how many of your parents would love to hear that? Yeah, I didn't think. Your mom, really?
Yeah.
Will they tell you study too much?
Well, yeah.
They do, wow.
But like, it would rather me hang out with them.
I totally agree. Oh, hang out with them?
Yeah.
Oh, every parent wants that, and no teenager wants that. So good luck with that. But the reality of it is you got one hand that you're saying 300 minutes and I'm saying 200 minutes. Why is mine better? Because you're doing it at one time and I'm telling you to do it 10 times. So you're operating off of volume and I'm operating off of repetition. And the reason why repetition matters is that every time you're accessing that neurological network, that very specific pathway, you're actually strengthening that pathway. Everybody following me on this? So this is why we say practice doesn't make perfect. I think that's a stupid statement. Practice makes permanence. This is why my family is a military family. Anybody have family members in the military or been exposed to it? What do the military members do? Drill, 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 over and over and over and over until they're just, okay, why do we have to do this for the 100th time? Why? Because when bullets are flying, they know exactly how to operate. Because it's become permanent in how they perform. This is what I'm trying to get across to you when it comes to studying. Every time I introduce something new to you, if you don't study it through repetition, you're not going to be able to access it. You're going to think, and some of you are like, this one, it's on the tip of my tongue. You ever heard somebody say that? Like, ooh, and they start snapping their fingers. I don't know what that does. All right? I don't know if they're just buying time or distracting, like, ooh, it's right there. All right? Or they say, and then they start looking up. You ever notice that when people look? They're looking to the left, they're lying. They're looking to the right, they're making it up. They look up, they don't know. And if they look down, they're embarrassed. You know what I'm saying? If they look right at you, it's fight or flight, all right? Male lion's about to fight. No, the fact of the matter is, though, is that when we start thinking about that distance, here's my big takeaway for you for learning. Reduce the size or the distance of your synaptic cleft. And if you don't believe me, there's actually studies being done where they have mice and they put them in a maze and they put cheese or some sort of reward at the end. But there's only one way to go through the maze. Everything else is blocked off. Now, the first time the mouse does it, they time it, takes forever. Second time, time reduces. Third, fourth, fifth, sixth time. Eventually, they put the mouse in there. What's the mouse do? Goes right to the cheese, instantly. But then they go into the brain of the mouse, and they remove very specific proteins that basically, like glue, keep that synaptic cleft so close. They remove that protein. What do you think happens to the mice? They completely forget how to get through the maze, even though they've done it hundreds and hundreds and hundreds of times. So my point is that the more you study things, the more repetition. This is why I keep telling you to speak it, to teach it, to go over it. You're literally, physically reducing the distance of your synaptic cleft. And the reason why that matters is that the further away they are, all of these ions and neurotransmitters can get lost. Now let me tell you what I mean by that. I'm going to restart this, and what I'd like you to do is watch, let me get rid of all these, watch these vesicles. They're going to migrate, they're going to move here, and they're going to go through exocytosis and look at the synaptic cleft and watch those tiny, they're hard to see, tiny little red spheres, and pay attention to these two proteins. These proteins here are called ligand-gated ion channels. Now watch what happens. Okay, so now you see they moved out, and now the neurotransmitters are connecting to those ligand-gated ion channels. Now watch what the proteins do. What happened? They opened. So neurotransmitters don't actually go into the adjacent neuron or junction. All they do is they connect to the proteins, these ligand-gated ion channels. And you're smart people, and I've already taught you this repetitiously. All right? I told you that every time something binds to a protein, what happens? Changes shape. So what neurotransmitters do is based upon which neurotransmitter is being released, based on which neurological pathway, it's going to cause those proteins to open and signal that response. So that's why we call this a ligand-gated ion channel. The ligand is your neurotransmitter. The gate is whether it just opens or closes. So the ligand is what controls whether it opens or closes. What's the ion? If the neurotransmitter doesn't move in, what are these purple spheres that are going to move into depolarized. There it is again, sodium. So if sodium depolarized this one up here, it's going to depolarize down here too, right? So the ligand-gated ion channels open, and then sodium moves in. Look at the pictures that are right in front of you. It's exactly what it's showing you. All right? Just take a look at them. Just make sure you're labeling this correctly. So at the very, very bottom of that image, and let me actually pull this up so we can all be looking at the same thing. And I'm almost done here, so just hang with me for a second. Everything that I just described you in that video is exactly what you're seeing here. The message is received. All of these vesicles start moving along those microtubules through exocytosis. They're released into the synaptic cleft. They start locking on to the ligand-gated ion channels. They open. And then once they open, sodiums move in and depolarize the next cell. This is what we call synaptic signaling, a one-to-one communication. But that's why we're saying the further distance of this synaptic cleft, those neurotransmitters and signals can get lost. Right? They might not connect to those ligand-gated ion channels. You want to know a great example of how humans look at that and say, that's really cool. How can we manipulate that? I'll give you an example of a great neurotransmitter. And my AP Psych students, you should know this one. Serotonin. What is it? Anybody in here take AP Psych? Okay, so if you took AP, what is it? Yeah, serotonin is a feel-good, right? It's a relaxer. It's a feel-good one. It kind of relaxes the body. Hey, man, yeah. All right, everybody feels good. Now, for the record, because I know I'm on video. Hey, Mom. All right, I know that when I'm on video, got to be careful what I say, I am not endorsing this. And for the record, never once have I done this. I can tell you that as an adult, I have drinking adult beverages, but not once in my life have I ever done drugs. Never. And the reason why is I study them and say, woo, that sounds terrible. However, this one, to a lot of people, sounds amazing. There's one where the serotonin floods the synaptic cleft, but then you take a drug to block the reuptake of it. What does that mean? Just like we said, when sodium moves in, we want to pump it out, right? When those neurotransmitters flood the synaptic cleft, do we want them hanging out there? No. Well, sometimes we do. Based in this case, if you're doing drugs, you probably want something to happen. But in this case, that serotonin floods, does its business, and then gets sucked back up into the synaptic bulb. This is what we call reuptake. Anybody know what drug I'm talking about? It's called ecstasy. It's exactly what it is. Ecstasy blocks the reuptake of that neurotransmitter. So when you're on ecstasy, and I know I'm not glorifying this because I'm going to circle back, tell you why you shouldn't do it. But that ecstasy blocks that reuptake, and your body is constantly flooded with serotonin. So everything feels good. All right? Now I know that sounds like I'm selling it, and I'm really not. Because ecstasy, because of that, it also, all those serotonin molecules, they change the electrochemical gradient, the cells stop behaving, and cells start dying. So literally, when they do contrast MRIs of the brain of people on ecstasy, there's little parts of their brain that are just blacked out. There's no activity happening. All right, and typically, they're in those lobes that control, sensations and things like that. So that's kind of my just say no. Sounds great, but it will kill you. All right, it will kill you. So that's the explanation of what we call ligand-gated ion channels. So it is receptor mediated. The ligand has to be there to open that channel. But for fun, let's test your knowledge of some neurotransmitters. You ready? Let's play a game. Here we go. Tell me what this one does as a group. What is it?
Pain relief?
Pain relief. Very good. All right, endorphins. All right, have you ever smashed, hit your toe on the corner of a table or something like that? Hit your finger on something, right? Why do we always shake it? Nobody knows. Doesn't do anything. But eventually that pain subsides. Doesn't mean that it's not effective. No. It just means the pain goes away. Why is that? Well, the evolutionary idea of endorphins is it allows us to get through the pain impulses so we can focus and get to safety. So whatever it is that caused that pain. So yes, that is a pain inhibitor. that they actually do this, and again, I'm not advertising this, but I have a couple of buddies that went through Marine training, and one was a scout sniper. And so one of the things that they tell them, like specifically high-level soldiers, is that when you're out in the desert, the jungle, wherever you're at, and you haven't slept in 3 or 4 days, the thing that they tell you is take a knife and just cut your arm. It's going to alert all of these neurotransmitters and wake you up. That way, because the last thing you want to do is close your eyes and then the enemy's right on top of you. So knowing how the body works sometimes, either that sounds kind of archaic, but it happens. All right, what about this one? Acetylcholine. I'll give you a hint. This one is blocked while you are dreaming. You're in stage 5 of your REM cycles. What's that? Yeah, you are literally paralyzed while you're dreaming. So what we see is a blockage of acetylcholine, which causes muscular contractions. How about this one?
Addiction.
What's that? Well, it can be addiction, yeah. All right, or sometimes even we see this in a lot of disease like Huntington's disease and things like that, but this is also emotion, personality, happiness. All right, if you are sad, your dopamine is low. So what do? You find something that ups your dopamine. Could be mood food, chocolate, ice cream, things like that, or whatever else makes you happy. Your happy place. You know how people tell you that? Find whatever makes you happy, you're increasing your dopamine. All right, next one. Serotonin, we already did that one. That's the one that makes you feel good. Get a good massage, turn into a wet noodle, you know what I mean? That kind of thing. How about this one? Yeah, that's your circadian rhythm. See, a lot of you say sleep. It's not. It's everything. It's your entire circadian rhythm. How you're. I'll tell you this. My melatonin right now is just jacked up because I stayed up till 3:30 the other night watching the election, just waiting to see what happens. Because yeah, it was pretty stupid, wasn't it? I don't know why. You know, the whole time I'm telling myself, because you kind of knew what was going to happen, but it was like a movie that you've invested a lot of time in. And it's starting to suck, but you want to see it through, you know what I mean? Just because I've already invested so much time. So I was kind of like one eye open. I'm like, I'm going to pay for this. So last night I fell asleep at like 7:30. And my wife was like, where'd you go? I was like, I was in bed. I don't even know what was going on. I was like, y'all are on your own. I don't even think I ate dinner. All right, so anyways. Okay, what about epinephrine? We talked about that one, fight or flight. What about norepinephrine? That's a challenging one. It's not so much an antagonist. Norepinephrine's kind of like a Swiss Army knife of neurotransmitters. It controls a lot of different things. It controls moods, arousal, sexual interest, all sorts of stuff. Okay? So, again, you don't have to memorize these. I'm not going to put your feet to the fire and say, what are these? All right? But I will tell you they are important to know just to understand how they're actually triggering a lot of our activities. Now, what are we going to do with this? We are going to, because of timing purposes, and I know you're all going to love this weekend, you will have a virtual quiz on Canvas. It opens up at 4 o'clock and it closes. Hear me when I say this. Closes at 11:45. And it will close even if you're in the middle of the quiz. Everybody with me on this? So you can't start at 11:44 and think you snuck in and be like, hey, it's going to stay open. It'll close at 11:45. And I'm not going to listen to any excuses about why you couldn't do it. All right? So my advice, get it done, get it over with. Of course, you're going to have all your materials in front of you. I really don't care. I just want to make sure we're getting this. All right, so make sure you focus on that. But that quiz is all about neurons, neurotransmitters, sodium potassium pumps, ligand-gated ion channels. All right, everybody good with that? Okay, so what we're going to do next is we're going to switch gears, but I know you're going to love this. If you have a calculator, I need you to get it out because we're going to do some more math. Well, that was pretty good. I've gotten that without any groaning. Usually when I say math, I was... All right. Now I could stand up here and talk your ears off for another 45 minutes about the signaling pathway of the cell cycle. And I will eventually get to that, but I don't want to focus too much on that right now. What I want to focus our attention on is why do we study it in the first place? Why do we care? So for example, when we talk about the cell cycle, And again, I don't say these things out loud to disparage anybody else, but your freshman year, how much the teacher went over cell division with you and how much time you spent on it is not good. You didn't do it enough, is what I'm saying. Usually it's at the end of the semester and everything felt rushed, right? And you just like a week and like, hey, these cells divide and da-da, and you prophase, metaphase, anaphase. Remember all that? Well, here's my question to you. How do those cells know when to divide? How do they know when to stop? You learn prophase, metaphase, anaphase, telophase. Within all of those divisions or stages of division, how do they know to have the nuclear envelope disappear? How do they know for the centrioles to build microtubules? Well, it's all part of the communication. That's going to be our third level of communication. But we're not going to talk so much about the communication today. We're going to talk about how we can measure if that communication is working. You have seen this, you just didn't realize you were looking at it. So right now, if I were to have you look at this picture, and I would ask you, is what you're seeing match what you expect to see? Let me put it another way. Do you think these onion cells, that there is something wrong and there's a mutation and it's creating a problem with its reproduction? Now, this is why I love all of you, because you're like so intent. You're leaning in, like, oh, what is it? What is it? You don't know. That's okay. You don't know. Because how would you know? Do you know how many of these cells you expect to be in anaphase? Would you believe me if I told you there's an actual number based on the rate of reproduction? So what percentage of the cells are in prophase? What percentage are in metaphase, anaphase, so on and so forth? So let's try this. What if I told you that this one right here and this one right here, those are your anaphase. And I'm observing two anaphases. What if I told you that there should be 10? Would you say that there's something wrong? I'm trying to see your eyes. I want to know what you think. And there's a reason why I'm going to bring this up, and I'm going to yell at you a little bit for a second. All right, not you, but your generation. It's actually not your generation. Adults suck at this too. All right? But back to my question. There's 2, should be 10. Is there a problem? See, I'm so glad you said that. All right? See, automatically, when things don't match exactly what we expect, we think there's some wholesale problem. But you just made a claim that there is a problem, but what do you lack? You lack data. You lack quantitative evidence. So I'm going to take this word and I'm going to put it in the mitochondria pile of things that you can and cannot say. There's a word that I'm going to introduce to you today. We say it a lot, but now it's going to carry more weight. This word is called significance. So I'll put it like this. Do you think there's a significant difference between the number of anaphase cells that I see versus what I expected? Okay? Now, a lot of you, again, are saying yes. But you can't say the word significant unless you've actually run statistical tests. That's the point I'm trying to make to you. Why am I bringing this up? How can I extrapolate this to your everyday life? How many of you have, and it's just us in these 4 walls, and I already know the answer, so just be honest. How many of you ever made a claim, said something as fact to somebody else, maybe something scientifically, 9 times out of 10 it's scientific. How many of you have said something to somebody else as if it's scientific fact that you're the expert in the subject, but you never really researched it yourself? Come on. If you're not putting your hand up, you're lying. Because we've all done it. I've done it. All right? When I was young, and especially nowadays in your world, social media. Well, I saw a 30-second video on TikTok, and so-and-so said this. Taylor Swift said it. It must be true. Well, that's kind of where we need to be better as young scientists, because here's the deal. Those things that you said as fact, let's just be honest with each other for a second. Those things that you said as fact, was there any emotion tied to that? Was there any of your bias tied to that opinion? Right. Okay? And this is kind of what I've always tried to teach people. I don't want you to think like me. I'm not teaching you exactly what to think. I'm teaching you how to think. So don't just parrot what other people say. Have evidence and investigate it. Reason why I bring this up is that, especially in this school, this kind of stereotype I have, he doesn't believe in climate change. No, that's not true. But people come at me with data, and come to find out, there's other teachers in this school that have name dropped me too. And I'm like, oh, yeah, let's debate. Bring it. You know what I mean? Because I'll bring the facts. I'll bring the discipline. They're going to bring what? They're going to bring emotion. They're going to bring emotional opinions. And guess what? How much I care about your emotional opinions? 0. I don't care what your emotional connection is. I don't care what your opinion is. You know why? Because if you don't have data, your opinion means nothing in the scientific world. Now, as people, do I care about your opinion? Of course we do. Nothing but love. All right? But as a scientist, if you're going to come out and make a claim, you better back it up with data. Or else somebody at some point is going to make you look really stupid. All right? So that's what I'm going to show you today. Today, I am going to teach you how to calculate that significant difference. And some of you have had experience with this. This is called chi-square. All right? So, some of you are just going to walk out here. You don't care about us. That's not what I'm saying. That's probably what you heard, but that's not what I'm saying. All right. So, what chi-square is, and again, teaching math is not the most exciting thing. I've already told you this, but let me walk you through how this works. And I will do this with problem number 1. So go ahead and look at problem number 1. Problem number 1 states that in this scenario, that believe it or not, maybe you didn't know this about me, I'm actually a doctor and I moonlight as an emergency room physician. Did anybody know that about me? Yeah, it's totally a lie. That'd be cool, but it's totally a lie. But nonetheless, in this scenario, how cool that would be, is that I witnessed in 2022 that in the 4 seasons, I noticed how many number of bones that I set because of accidents or whatever. So it's provoking a kind of a question. Is there a connection between the season to the number of broken bones? All right. Now, this is what chi-square is going to do for us. Look over here. And this is things that you should be jotting down here. Chi-square is simply the measurement of the significant differences between 2 or more sets of data. The significant difference between 2 or more sets of data. Now, before you just keep writing everything, let me circle back to this one more time. When I showed you this image, look over here. When I showed you this image, you really have 2 choices. Is there a significant difference between the 2 that I see versus the 10 I expected? Or do you think those differences are simply random? Because we know that it's not always going to match what we expect. But is it significant enough to say, wow, there's something really happening here? So for like these cells, it could be a new fertilizer. It could be a mutation. It could be pesticides. It could be whatever the case. Whatever's causing this change. So that's what we're going to measure using chi-square, is that significant difference between quantitative data. So we set this at 0. What do I mean by that? We set a null hypothesis at 0, which means we assume that everything is random. Everybody get with me so far? If you assume that everything is random, when it's significant, there's no arguing it. So a null hypothesis states that your independent variable does not impact your dependent variable. There is no connection to that. So in this case, do you think, based on our null hypothesis, look at question number 1. What would our null hypothesis be? Do the seasons have any impact on the number of broken bones? No. Our null hypothesis would state that the seasons, because that's your independent variable, have no impact on the number of broken bones, which is your dependent variable. Remember, your dependent is what we're measuring. That would be your null hypothesis, and that's what we're trying to test. We are testing the null. Now, look at your normal hypothesis. What would you say if you were to write a normal hypothesis? Do you think there's a connection? Sure. So you could just rewrite that. If we study the different types of seasons, then what would you say? Maybe summer should have, there is a connection between the seasons and the number of broken bones. However you would say that. However you write your hypothesis statement. All right? So that's what your hypothesis is, but your null hypothesis is no connection between your independent and dependent. All right? So this is how we run these numbers, and I need you to follow closely here, or else you're going to be lost. There are parameters to how you set up your problems. The first question is, what are your degrees of freedom? Now, degrees of freedom, as you can see behind me, is n minus 1. Why minus 1? The n minus 1 maintains randomness. And what do I mean by that? If our null hypothesis states that everything is random, whatever parameters we set up has to maintain that randomness, correct? So let me give you an example of what I mean by degrees of freedom. All right? I have a bowl of M&Ms. There's only 6 in there, one of each color. I blindfold you and I say, grab an M&M. What color do you draw? What do you think? What color would you draw? Blue. Good choice. How do you know that? You don't. All right? There's no way of knowing. The M&M you draw is random. Now, do you have a probability? Sure. But it's still random, isn't it? Okay? Throw that one out. I have 5 left. Draw another one. Which one do you get? See, we're getting better at this. Okay, you still suck at this. All right? It's still random. Okay, throw that one out. Let's try again. I have 4 M&Ms now. Hey, there we go. All right, we're learning. See? Practice makes permanent. Your synapses are getting closer and closer and closer. All right? So the fact is that every time I draw an M&M, it's random except for which one? The last one. Because now I only have one M&M in there. It's not random anymore. So I have to eliminate that from my data set to portray randomness. So that's why we always take n minus 1. So look at problem number 1. You have 4 data sets: spring, winter, summer, fall. That's 4. Subtract 1. So what are my degrees of freedom here? Go ahead and write that down. Your degrees of freedom would be 3. So always figure out how many numbers of data sets you have, and then subtract 1. That's going to maintain randomness. Okay? Your p-value, go ahead and jot this down. Your p-value is always 0.05. Always. Now, what is our critical value? And I'm going to explain this a little bit because we're going to work on this problem together. But everybody look at the top of your paper I've given you. This is what we call a critical value table. Now, to determine your critical value, you take your degrees of freedom, so in this case 3, and you move over here until it intersects 0.05, which is our p-value. That's just a kind of a parameter we set, a percentage of error. All right? So right here, your critical value is 7.815. What's that number mean to you? Anything? No. All right? Here's what the critical value means. And I'm going to keep this as simple as I can. So in this case, from 0 to 7.8149999999, from 0 to that number, if our chi-square value is between 0 to that number, it is still random. This critical value, this is what you should write down, is the permitted randomness allowed. So if I go over 7.815, is it still random? No. That's the point of the critical value. If it's below my critical value, it is random. If it's above my critical value, it is significant. Everybody with me so far? All right? If I'm not explaining this right, make sure you're asking questions. All right, so this is what I want you to do. Go ahead and look at your data table, and go ahead and write in the seasons and then the number observed. Go ahead and do that now. I guess I'll put it. Okay, so we got spring, winter, fall, obviously order doesn't matter here. So spring is 59, winter is 39, summer is 92, and fall is 55. All right, now let me ask you a question. Do those numbers make sense to you? What do you think? They don't make sense to me. But I grew up in probably different areas than most of you. When we think number of broken bones, what would you relate that to? Why are people getting broken bones? Maybe they're outside more, right? They're out playing soccer, they're playing their sports, whatever the case may be. Maybe they're on vacations, they're going to Lake Lanier and getting pulled under by ghosts and things like that, and they're on, jet skis going 70 miles an hour, and then they wipe out, and then they bounce across the water, and then they get up and like, I can't believe I broke my leg. People like that. Okay, so that would make sense. But see, me, these numbers don't make sense because growing up in Michigan, it was snowy about, 5 months out of the year. Snow to us was just, that was like paradise because as soon as snow fell, you were on snowmobiles. Anybody ever been on a snowmobile in here? Have you been on a snowmobile? Really? They're fun, aren't they? Yeah. They're wicked dangerous though. Because if you're on the snow, you can't really see depth. So you're like, yeah, just fly over the handlebars or hit a tree stump. I've definitely done that. But also, snowfalls, snowballs. All right, I can neither confirm nor deny that I broke my brother's nose with a killer snowball. And I actually got in a lot of trouble for it. Don't do this. But I got a snowball and I soaked it with water. Then I put it in our fridge. And then it got really, really hard. And then as you walked around the corner, bang, right to the nose. Yeah, broke it. It was awesome. All right. So yeah, in my family, we had more casualties in the wintertime than we did the summertime. But nonetheless. All right, so what I need you to do now is that this is what I observe. Is that what I expect, though? What do you expect? If it's random.
They should all be the same.
Very good. They should all be equal to each other. If it's random and there's no connection between the season and the number of bones, they all should be the same. So you're going to calculate all of these as the sum, and that's going to be your sample size, and then you divide by 4. Go ahead and do that now. If it's random, there's no connection, they should all be equal. And everybody should have gotten 61.25. Is that what everybody got? Okay. Now at this point, you can go ahead and run your numbers. Now y'all are smart enough that you really don't need to do these two columns. All right, you just skip to this column here, but make sure you're following your order of operations. Observe minus expected first, subtract first, then square, then divide. So go ahead and calculate all 4 of those, and then we will come back together. That should take you about a minute or so. Bless. All right, does somebody shout out the number for spring for me? Is it 0.08 or something like that? Is that what it is? I'm just trying to do this off of memory. And then winter was like 8 or 15? 8.08. And then summer was like 15.43, and then fall was, what was that? 0.63. Okay? Now, as you calculate those, I mean, once we get this number, it's pretty easy to plug and chug. But remember, what am I doing here? These numbers right here are chi-square values for each individual data set. But now what I need to do is I need to create the sum of those. So add all those up and tell me what that number is. Bless you. It's that time of year. Everybody's starting to sneeze and get sick. Stay over there. Okay? So, you should have gotten 24.2 for your chi-square value. Is that correct? Now, what does that number mean to you? Absolutely nothing. And that's okay. That's okay. Because many of you, I think you did this your freshman year, right? You did it, but did it make sense? No, that's the whole point, is that everything we look at as scientists, there's an expectation of what we should see. But then we have to measure what we're actually seeing. And you're going to see how this plays out a little bit later on when we start getting into cell division. So this number, 24.2, what I want you to do now is compare it to your critical value. And as we just said, my chi-square value is greater than 7.815. So would I declare my data significant difference, or would I declare it random? It is significant, and that's where you can see right here. If our chi-square value is greater than our critical value, we reject our null. And now we can proclaim that something is significant. This is why I keep telling you, you have to have data to support your opinion. Not saying your opinion's wrong, but your argument is so much stronger if you have data to back it up. And if you're yelling and crying and screaming and kicking like a school kid, nobody's going to listen to you. All right? Nobody's going to listen to you. And here's why I'm banging the drum on this. You all live in kind of this vacuum right now of what people like to call misinformation. But if you keep calling everything misinformation, can that be factually accurate? Right? So even if it's misinformation, why do people call it misinformation? Because it doesn't align with what your opinion is. Right? So rather than argue it with facts, data, what do people do? They get pissed, they get mad, and what do they call it? You're lying. It's misinformation. And then automatically, as soon as you say it's misinformation, nobody's going to listen to it anymore. And that is a dangerous precedent. You know how I know this? Because it used to be called misinformation when people were teaching kids that the earth was ovular instead of flat. It used to be considered misinformation to tell people that you should wash your hands or else you're going to get sick. Now what do you do, or should you do, multiple times a day? Wash your hands. That used to be considered misinformation. So just because it doesn't line up with your personal opinion doesn't make it wrong. That's the point. But that's science, is that we should be able to argue and discuss and debate and have these opinions, but as long as they're rooted in scientific data and facts. Right? Because at that point, that's why I put that right there. Without data, you're just another person with an opinion. And you're entitled to that opinion, but that doesn't mean people have to listen to you. And they're not going to take you seriously. Okay? So that's why right here we see this, and we can now say unequivocally we reject our null hypothesis, and there is a significant difference. So does the number for summer make sense now? What we can say is that the number of broken bones is tied to the season because of maybe you're outside doing more activities, stuff like that. Okay, so I know you're tired of listening to me, so I'm going to have you work on these the rest of the period. Like I said, I don't want to bore you to death with all the other cell division stuff and communication. So we need to be really good at these because we're going to be doing a lab on this. We're going to be doing more problems on this because this is what we're going to be looking at in terms of how we understand the cell cycle and its communication. Okay, the only thing I'm going to give you some advice on. Look at problem number 2, and I just copied and pasted, so that just disregard that where it says number of broken limbs. This one is talking about visitors and number of people to all of our locations here in Atlanta. Okay, I'll let you figure that one out. But then we get to this one, and this is an old friend of yours. Punnett squares. Remember those? I hope you enjoyed Punnett squares. You know why? Because in my classroom, you're never allowed to use a Punnett square ever again. Now I'm going to teach you how to do it in your head so you can work faster. Because you know what a Punnett square is. A Punnett square, all that is an expected value. So, for example, all right, enjoy this because this is the last time we're allowed to do this. When I cross those two, without doing a Punnett square, what's my ratio? Do it in your head. Oh, this is going to be fun. It's 1 to 2 to 1. Very good. Now, those of you who don't believe me, you're like, no, man, I need my Punnett square. All right, and then I do this. So, right here, all right, you got your 1 to 2 to 1 ratio. So that means 25% of the time, I expect to see homozygous dominant. 50% of the time, I expect to see heterozygous dominant. 25% of the time, I expect to see homozygous recessive. That's how you calculate your expected values for genetics, is you use your ratios that you should already know. 1 to 2 to 1s, 9-3 to 3 to 1s, all of those. So that's how you figure out your expected values. And that's where I'm going to leave you with that. So the last 30, 35 minutes, work through the remainder of these problems. There's only 3 of them. You should be able to get done with them. All right, so have that done before I see you again. You will take your quiz on Monday. This weekend. And then on Monday, we're going to look at both of our quizzes, 3.1 and 3.2. We're going to look at both of them in class. All right, so we can start moving on into our last quiz and our last little section of this. All right, we good? We know what we're doing? All right, get to work. Let me know if you have any questions.